Yes, I'd like to talk about some of my favorite, let's say, research topics and what I've encountered since I started my studies. But there's so much to talk about, so it will be a little collection of things that I really enjoy, and I hope to share this with you. And to start, we have, I first make sure it works. Okay. So, yes, that's better. So, to start, all this is possible thanks to space exploration. And in 1969, Neil Armstrong made his first step on the moon. And 30 years later, this is a quote that he had for a press conference. In my own view, the important achievement of Apollo was a demonstration that humanity is not forever chained to this planet, and our visions go rather further than that, and our opportunities are unlimited. So it's not the most common quote that we know. Small step for man, a giant leap for humanity. But this is perhaps more a vision of space exploration that I think is happening right now. So Neil Armstrong died on the 25th of August 2012, and I would like you to keep this date in mind. So I think a lot of you are familiar with the sun, although I see a young person over there, but I think a lot of you are, some of you told me they are amateur astronomers. And the first thing that amateur astronomers can share is the Carrington experience. So in 1859, Carrington observed the first solar flare, and this was an observation of the photosphere, where you can see the sunspots here. But what's truly a life experience, if you're an amateur astronomer, is to point your telescope one Sunday morning, and then to find that you've got an X-flare happening. And this is what happened to me and friends when we visited some amateur astronomer who had its own telescope above his house. And this is different than looking at the sun through a telescope. And it's really something you can do. But this was happening on. You can do it, but you have to be lucky. This was happening. This was the moment where the solar activity was rising. It was in 2011. We had been in a very deep solar minimum, we call it, for the first time in many years. We didn't see much activity, and so this was a very nice thing to see. Now, I mentioned the photospheric layer. So this is the surface of our sun. It's about 6,000 Kelvin, 7,000 degrees Celsius almost, for those of you who don't know. But what's happening after that is truly a puzzle. The temperature is rising. So we start to see what we call the chromosphere, and higher up the corona at 1 million degree Kelvin. So this movie was showing that flare that happened, that we observed, and I can play it again. But maybe you could see. Very bright flash. So this would occur at temperature of 10 million Kelvin, so another scale. And we measure the flare in a full full disk measurements in X-rays, and we classify them. So there are different classes, A, B, C, M, and X is the top one. So this, when this happens, it's quite a nice thing to see. Now, the flares and their associated coronal mass ejections, they are the most important, but so far the most difficult space weather events to predict. So I mentioned this flaring events in the extreme ultraviolet that you can see in some observation, some layers of the corona. Then this was an event that was associated with the coronal mass ejection, and you could see this movie happening here, where the disk of the sun is occulted by this occulting disk here. Now, at a different radial distance, we start to see a halo coronal mass ejection that travels towards Earth, and particles are being accelerated and hit the spacecraft and the instruments, and so this is why you see this kind of snow event. So this can go very fast, and I mentioned the solar energetic particles that hit the spacecraft, and you can see in this event, which happened in 2003, we had energetic events that happened about 17 hours from the start of the flare. And this was so large, it was out of the scale. So this event caused damage on a spacecraft that was next to Mars, MARI 2001, MARI instrument on 2001 Mars Odyssey. And what I'm showing now is a movie of a portion of the sun taken by the Solar Dynamics Observatory. It's a new telescope that's been launched in 2000. That started to take pictures in 2010. And what you could see here, where you had some flare pushing out some plasma, and then oscillations in a loop, on the coronal loop. These are the kind of motions that happen all the time in the corona, and they are interesting to follow and to look at, because they could lead to instabilities. So here I'm talking about flows and forces due to these motions that can trigger some eruptive events. So this is interesting to have a look at the activities, monitoring what's going on, and see maybe whether we can gain some knowledge and say later, okay, this particular region will erupt. So one of the aspects I find very interesting is the Kelvin-Helmholtz instability phenomenon. So this is a phenomenon that you must don't realize you know already. This is something you see at the interface between the sea and the air. So the waves, they are Kelvin-Helmholtz waves, and also in the clouds, for instance. So and the interface between the clouds and the air. So it requires a flow shear, so a difference in flow. And so this is a very common phenomenon in the atmosphere. We find it also in the atmospheres of giant planets like Jupiter. Jupiter has this big spot where you can see these vortices. But what's more difficult to understand is how it's happening in the magnetized plasma, in the environment of the solar system, for instance. But it's happening everywhere in the astrophysical environment. So I mentioned the solar corona. I mentioned the magnetosphere, this bubble that protects us from the solar winds. the heliosphere, I will talk about this later, the comets, and astrophysical phenomena like astrophysical jets. Now, what's happening here? We have a simulation that shows two plasma with different densities and a shear flow between them. So what's happening here? We have the Kelvin helmholtz developing, and each different plasma has a different magnetic field. So initially, the magnetic field can be parallel or different direction, and when the Kelvin helmholtz vortex roll up, this magnetic field can be in contact with a different orientation. This is something that you don't find in the atmosphere. You don't have the magnetic field. But what it brings in the solar plasma is an opportunity for magnetic fields to reconnect, and for when you get reconnection between magnetic fields, you open a hole, if you want, between one region and the other. So you allow one plasma to mix with the other. And this is very important, for instance, in the magnetospheric context, where you would have solar wind plasma being able to enter into the magnetosphere. So it's important for us to understand this phenomenon and why it could lead to the formation of so-called boundary layers between different plasma. And it goes on to, this is called, in a magnetized plasma context, it's called magnetohydrodynamics. So instead of hydrodynamics, we have magnetohydrodynamics, MHD. And it goes on to develop and to merge and to decay into smaller scales. And so there is a lot of turbulence that can be generated. So this is an interesting phenomenon. There are lots of different things happening in magnetized plasma, but that's one that I felt most interesting. And in the past years, I felt I could see this almost everywhere. So I wanted to first show you something about what we call prominences or filaments. So the prominences are cool and dense clouds of plasma that we find in the solar corona, and they are hanging there. And this is what we can see. We can see them in an eclipse, a solar eclipse. Now, we can observe them on disk, and they are called filaments. And these filaments from the ground, they've been studied quite extensively. From the ground, you can observe the sun. You have less than 12 hours to do so, depending on the season. And then you have to wait a night, and then you have to come back and study it again. If you go from space, then you can see this. From space, you can look at the sun, and instead, for instance, here in this extremely ultraviolet image, you would see the filaments, but it would be seen in absorption. And you can follow this filament, prominence if you prefer. And following this filament as it crosses the disk, you can look at its dynamics over 13 days, in fact, because the sun rotates with about 27 days. So doing so, it was possible to look at variability of the prominence. Now, if you zoom in on a prominence like this on the limb, you may zoom in with telescopes like INODE that also are quite recent. And this one is showing you a movie of the prominence. So I'm going to, and you can see these rising plumes. These rising plumes, this is the solar surface. Sometimes you also have some kind of bubbles. We believe that all this is due to flux emergence from the solar interior emerging. And so here we had some what we call plumes at the base of these bubbles, and they sometimes form some mushrooms. So that's one of these mushrooms that I showed earlier. So this one is showing you the mushroom that at the end of this so this is more difficult to see with the light. So this was another spacecraft which was launched in 2006 is stereo, and this is really a fantastic mission. It doesn't have all, there's better instrumentation, but what it did was you have two spacecraft. It's to go away from the Sun-Earth line. So until now, for instance, with Inode, we are watching the sun just in front of the Earth. Now, this spacecraft ahead is going ahead of the Earth, and it's stereo A, and this one, stereo B, is going behind. And in February 2011, these two were exactly in quadrature. So for the first time, we were able to see the 3D we were able to see the back of the sun. So we had a full 3D picture, 300, each 180 degrees separation. Now, these spacecraft are continuing their trajectory towards the back. So at some stage in 2015, they're going to meet up and they're going to continue and cross over. But this is really the extended mission. So we don't know yet what's going to happen. Now, we are here in 2014. I'm just showing you where they are in 2012, a little bit behind this quadrature. What do we do? Initially, with two views with stereo in the beginning of the mission, this was to do a reconstruction and understanding where is plasma going. In particular, I mentioned the prominences. They erupt. They form what we call the coronal mass ejection. And so, having the two views, we are able to see in which direction this prominence was going, in which direction the coronal mass ejection was going, and whether it would travel towards the Earth, which is very important if we want to do space weather. Now, another mission is the Solar Dynamics Observatory, and this one is pretty remarkable because it has a spatial and temporal resolution that's not as good as any other spacecraft. Not that it's some spacecraft can have a good spatial resolution, but it has this resolution of the full disk. So it takes these images. So you can see there are 10 different band passes, and we can look at the photosphere, the chromosphere, the transition region, and the corona in the higher temperatures. So these are the different band paths. And so when we, in 2010, so it was launched in 2010, when one eruption, a coronal mass ejection, occurred for the first time on the limb, what was very interesting was to observe the first time the magnetic Kelvin-Helmholtz instability. So I mentioned this. The CME is a source of flow, so it goes very fast. This one was going at 800 kilometers per second. And if if you look at this movie, you don't have the time to notice this Kelvin-Helmholtz instability. You really have to take picture by picture, take a snapshot, little box here along the flank. Show it every 12 seconds. And then what you see the ejecta front at 800 kilometers per second. And then these ripples here. And if you follow the speed of these ripples, so it's a distance time plot, you find that they are about half the speed of the ejecta. And this is what we expect from theory. So this was a nice observation. Once you understand the implication, you understand how important it is. The fact that you have Kelvin-Helmholtz is that it can have an effect on the drag in the CME. So the CME, you have more inertia because of these waves. Now this was observed only on one flank of the CME. So you can see that this side will go less fast than the other one. So you expect the CME trajectory to be deflected, this side going faster than the northern one. And this can be interesting to explain the differences in the drag properties between CMEs. So this is something to take into account if we want to look at trajectories of CMEs. So in this event, this movie was playing, showing the corresponding coronal mass ejection, and you can see that the CME is quite in the equator, while initially the direction was more southward. So there is some observational evidence. Now, I'm talking about future science. Solar Orbiter and Solar Probe Plus are two missions that will be launched in 2017 and 2018. And this is an artistic impression of how close Solar Orbiter will go. So we have here Solar Orbiter orbits showing that it will go as close as about a third of the distance between the Sun and the Earth, so 1 astronomical unit, and so a third. And but also with some successive gravity assists, the orbits will be shifted in latitudes. So we are going to have a view of the polar regions of the Sun, and that's very interesting because we haven't been there. With stereo, we were able to go all around, but we haven't been above. And it's when we observe the Sun, it's always you don't have as good resolution when you look at the poles. And the other mission happening at the same time will be complementary, and we'll go even closer in the solar corner at about 9 solar radii. So this is the future for solar physics. And now I'm going to talk more about the solar wind and the heliosphere. By the way, this is a nice picture of the comet Magnotte. So the Sun and the interstellar medium compete for control of the interplanetary medium. So this is a logarithmic scale. This means here you have 1 astronomical unit, Earth, 10, 100. 100 we expect to be at the end of our heliosphere. So this would be what we call the heliopause. Then we are in the interstellar medium, not necessarily outside of the solar system. So the solar system is still influenced by the solar gravity. So why is the heliosphere important? So the heliosphere is important because it's our first line of defense against cosmic rays. And what you have here is a fraction of galactic cosmic rays prior to the heliopause, and then as it reaches the Earth, maybe you get about 25% left. And matter plasma cannot mix. So I mentioned the Kelvin-Helmholtz instability as a way to mix the plasma, but in normal conditions, so you cannot mix when you have a boundary like the heliopause. So we have a balance between the solar wind, which exerts a pressure, and the outside interstellar medium pressure. I also mentioned some earlier results from missions like ULYSSES. So we haven't had telescopes going and looking at the poles, but we had the mission ULYSSES that went in situ and make measurements in situ of the solar winds. And what ULYSSES found was that the solar wind was much faster above the pole than in the equator. So there is a difference in solar wind speed, much faster, 800 kilometers per second, 400, 300 in the middle. And this is because from the coronal holes, we have open magnetic field lines. So the fast flows can go out much easily. Sometimes the coronal holes go towards the equator, and then sometimes these fast flows arrive at Earth and cause some disturbances because they are much faster than the normal solar wind, which flows out more slowly and is connected to closed loops. So what is the solar wind doing? Well, this one actually is not the solar wind on its own. Imposed on the solar wind, we have this coronal mass ejection that I mentioned. And so this is a movie of a comet by Stereo A, and it captured the first images of the collision between coronal mass ejection and a comet. This was the NKS comet. We have also a movie that describes the interpretation of this observation. So you can see this comet propagating, and the coronal mass ejection disrupting its tail. Now, the same comet, you can see the comet just without CME, just floating about in the solar wind, and its tail is flapping. This flapping of the tail has also been interpreted as to do with the Kelvin-Helmholtz instability. Because you have changes in the flow, you can have these motions. Now, there are several telescopes on stereo, so they are all put together. They are different field of view. And somebody showed me a picture of an aurora in Melbourne in March 2012. Well, you see this was from March 2012. So we have the sun here. We have the Earth. We are seeing from stereo A in 2012, remember, we have this view almost at quadrature, so we can see very well the Earth, the Sun-Earth alignment. And during this period, you had many X-class flares and coronal mass ejection. So this is what's happening to our environment. Okay, so here I think we had Mercury, Venus, and Mars. And so all these CMEs are coming out. And now the question is, what's happening to them? Okay, they're going to disturb the tails of comets, they're going to create displays, auroral displays in our heliospheric environments, but where do they go beyond the Earth, beyond that? So what happened also very recently, actually on 25th of August 2012, remember that date, it was when Neil Armstrong died. Well, this Voyager crossed the heliopause. Now, it was not very clear that they crossed the heliopause on that date. It took a while to be convinced. But I think now they are quite convinced about it, and I'm going to show why. There's a lot going on at the moment with another mission called the Interstellar Boundary Explorer, and it does some kind of imaging of the heliopause boundary or heliosheath boundary, and it shows some interesting ribbon. Oops. Okay. Well, I let you listen to this movie. They talk very fast, so they tell a lot of information, and I probably can hear more.
The Interstellar Boundary Explorer, or IBEX spacecraft, is unique in NASA's heliophysics fleet. Instead of studying the face of the sun, IBEX looks at the very edge of the sun's reach, starting at about 8 billion miles away. The region begins with the termination shock, where the solar wind abruptly slows down. It ends with the heliopause, the boundary between the solar wind and interstellar space. Between the two is the heliosheath, a teardrop-shaped region sculpted by the pressure of the interstellar medium. IBEX is also different because it makes its images from particles instead of light. Some of the atoms it detects originally came from the sun as charged particles, traveled out to the heliosheath, bounced back, and gained electrons to make them neutral. Others were neutral to begin with and came from interstellar space. Both kinds are called energetic neutral atoms, or ENAs for short. Over the course of 6 months and many orbits, IBEX can paint a picture of the entire sky in ENAs. For easier viewing, the sphere of the sky is unwrapped and projected onto an oval, much like how a map of the spherical Earth is projected onto a rectangle. The colors correspond to how many atoms hit the detector from a particular region. Violet represents few atoms, and the colors move up to red, which represents many atoms. IBEX can also tell how energetic each atom was, and, much like filtering light to show one color, create an all-sky map of each energy level. Viewing the sky this way can reveal some startling things about the edge of the solar system. IBEX is led by Dave McComas of the Southwest Research Institute in Texas. Its first major discovery was a ribbon of bounced ENAs showing unexpected activity at the edge of the solar system. Subsequent measurements show that this ribbon changes over time. IBEX has also measured ENAs from the interstellar wind, giving scientists a clearer picture of its composition. Surprisingly, it turns out that the local interstellar material is different from the sun, and the wind is slower and coming from a different direction than previously thought. Closer to home, IBEX has used ENAs to help understand the Earth's magnetosphere better, and has even observed the solar wind reflecting off the moon. As IBEX continues to scan the sun's horizon, who knows what other discoveries it will make?
So, I think it was a way to explain this IBEX ribbon in a quicker way than I could. So, but the IBEX ribbon is believed to be due to the interstellar magnetic fields outside the heliopause. And so what the movie was telling you about was that the interstellar flow is much slower than expected before. And instead of having what we called a bow shock, we believe that now we don't have a bow shock in front of our heliosphere, but we have a bow wave. And the other result was that this region is a very dense and hot region, and it's due to a pileup of this interstellar gas, and it corresponds to a broadened hydrogen wall. Now, this is important because to understand what Voyager sees, to be able to say that we have crossed the heliopause, we need to know that it's going to be very dense on the other side of the heliosphere in the interstellar medium. And what I'm showing here, I should stop a bit. Okay. I'm showing some measurements from Voyager, a radio plasma wave instrument. So I mentioned Voyager reaching the metropause in 25th of August 2012. Voyager was launched in 1977, September, so it took 35 almost years to reach the heliopause. But we were not sure that Voyager had crossed the heliopause because there was no real change in magnetic field direction and intensity. And a lot of the instruments are not working anymore, so there's not much to tell us about the plasma pressure and density. Now, earlier I mentioned the CMES of March 2012. What you see here are the response of the interstellar medium to the shock of the CMES hitting the heliopause. So the fate of the CMES of March 2012 is known in May 2013. So it took 13 months for the CMES to reach the 122 astronomical units and to give the plasma locally a response by vibrating. So the electrons that are attached to the ions are kind of vibrating, and we call this frequency the plasma frequency, electron plasma frequency. And this frequency is linked to the local density. So what you have here is although you see the frequency on one axis, what you see here is the density. So time after we had crossed the heliopause, there was probably another event here that shook the plasma. And then in May 2013, again, this response. So we were able to see this change in density also of about tenfold, right? So, and this was this corresponds to the broaden wall, the density increasing on the other side of the heliopause. So that was a nice result for Voyager. That means Voyager leaves the heliosphere, but not so much the solar system. So we are still under the influence of the solar gravity. Now, so I mentioned this broadened hydrogen wall, and this is something that helps us to see other astrospheres. So what we are observing with the Hubble Space Telescope are the result of these bow shocks from the interaction between other astrospheres and interstellar neighborhood. And this map actually shows you where people have detected these astrospheres, and also where people have seen some exoplanets. So apparently from that map, they said that there are 2 astrospheres with exoplanets, which is analogous to our system. So these are the kind of images that you see where stars are surrounded by astrospheres. So like the stellar wind would be before that. So this is the hydrogen wall beyond